Principal component analysis asks the following question. Can I transform my data in a different coordinate system and in doing so re-express the data as best as I can? And what we mean by best will become clear as we go on. Transforming the data means taking the values in the original coordinate system and rewrite them as values in a new coordinate system. On this figure, each point is a sample from our data set. Let's for instance take this point right here, which has an x-coordinate 6 and a y-coordinate of roughly 7. Let's call this sample point R. This point R would appear as a row in our data set, where our data set is a matrix of two columns representing the x-coordinates and the y-coordinates of each sample. And let's say x is height and y is the weight attribute. R would appear as a row in this matrix. Each of the other points in this data set, say this one here, would be another row in this matrix. If we transform the data to the basis vectors PQ shown here, we would be taking the x and y coordinates of each point and rewrite them as they would fall on these basis vectors. Let's take the point R, which roughly falls on P equals 5 and Q equals 1. In the original data set, we were able to say x is height and y is weight. But in this transformed data set, we can no longer say that. P and Q represent some abstract attributes. If we look at the direction of P, we may be able to say that P captures most of the height information and a little bit of the weight information. In PCA, we only do a linear transformation of the data. Linearity simplifies the problem and makes it so that we can easily compute the best transformation. But we have to keep in mind that after we transform the data using PCA and we don't keep all of the coordinates, we may lose any nonlinear patterns in the data. What does it mean to linearly transform a data set represented here as a matrix X? Let's say X is an m by n matrix where m is the number of samples and n is the number of attributes. A linear transformation is essentially a matrix multiplication with a matrix P, where P is an n by n matrix. Geometrically, P is a rotation and stretching of the space to transform X into Y. The columns of P are the set of basis vectors that we use to express the rows of X. The basis vectors that I showed in the previous slide would each be a column in this transformation matrix. In principal component analysis, we call these vectors the principal components of X. As you can imagine, there are an infinite number of possible transformations we can perform, each encoded by different set of numbers in a transformation matrix P. Which one is the best one? The main idea behind PCA transformation is to reduce redundancy in the data. In our original space, height and weight were somewhat correlated attributes. In a way, they are redundant. In our transformed space, the abstract attributes should covary as little as possible, such that each one should contain information not present in the other attributes. In other words, in the transformed space, the abstract attributes, the basis vectors, should be correlated as little as possible. The scatter matrix is another term we use for the covariance matrix. Let's use capital X to represent our original data set. And let's assume that we have already shifted X to its mean, which can be done by finding the mean value of each column and then subtracting that from every value in that column. After this shifting, the mean value of each column would end up being 0. Remember the definition of covariance? it was defined as the average squared difference from the mean. Since we made the mean 0, the covariance can now be written as the average of the square of the values. In matrix form, taking the square of the dataset means multiplying it with its transpose. We have m rows or samples in the dataset. Dividing by m-1 gives us the average squared difference. You would get the same scatter matrix if you did not shift x to its mean. Shifting to its mean is out of convenience of notation. X is our original dataset, and we don't really have control over the scatter matrix of X. It is what it is. The covariance matrix is a symmetric and square matrix. If our dataset is two-dimensional, the scatter matrix would be a 2 by 2 matrix. If our original dataset were three-dimensional, then its scatter matrix would be a 3 by 3 matrix. After we transform the matrix by multiplying it with the transformation matrix P and obtaining the transform matrix Y, we can calculate its covariance matrix as well. By carefully choosing an appropriate matrix P, we can change the matrix Y, and consequently we can change the scatter matrix of Y. Remember that our goal is to have the coordinates or the columns of Y correlated as little as possible. What would that say about the covariance matrix of Y? The diagonals of the covariance matrix will be non-zero values, and that is fine because each variable is correlated with itself. But the off diagonals should be 0, which would mean that these variables are not correlated with each other. They are independent. To rephrase our goal mathematically, we are trying to find an orthogonal transformation matrix such that after we multiply it with X, we get a matrix Y whose scatter matrix is diagonalized with non-zero values on the diagonal and zeros everywhere else. Let's work with the scatter matrix of Y to see what we can do. This is the definition of the scatter matrix of Y. I have removed 1 over m-1, which is a constant factor for convenience. It is just a scaling factor and will not going to change the fact that we are trying to end up with a diagonalized scatter matrix. I will replace Y with X times P because that is how the Y matrix is obtained. Rearranging these gives me P transpose times X transpose times X times P. X transpose times X is the scatter matrix of X. So let's write that instead. We are kind of stuck here. Let's see what else we can do. From linear algebra, we know that every real symmetric matrix can be diagonalized, meaning we can rewrite a real symmetric matrix using eigen decomposition as follows. Here E is an orthogonal matrix, where each column of E is an eigenvector of A, and D is a real and diagonal matrix, meaning it has some non-zero values on the diagonals and zeros everywhere else. The diagonal values of D are the eigenvalues of A. We know that every scatter matrix is real and symmetric, so we should be able to rewrite S of X using eigenvalue decomposition in this form. After we replace S of X with its eigenvalue decomposition, we end up with this equation for S of Y. Let's repeat our question. How can we carefully select P such that S of Y is a diagonal matrix? Well, let's see what happens if we select P equals E. We should have this. E is an orthogonal matrix, so E transposed is equal to the inverse of E. And when we multiply E transpose with E, we would get the identity matrix. Identity matrix acts like a 1 in matrix multiplication, so we can drop it out and we would end up with just D. Remember that D is a diagonal matrix, So we have accomplished our task of making S of y a diagonal matrix. By choosing P to be the eigenvectors of Sx, we have made Sy a diagonal matrix. So that's what we'll do as the best transformation that gives us a scatter matrix where different variables are independent. They have covariance or correlation of 0. The values on the diagonals of D, which are the eigenvalues of Sx, give us the amount of variance along each of the eigenvectors. This concludes our derivation of the principal components analysis. Let's summarize what we would do given a data matrix X which has m rows and n columns. Here I am showing a matrix with n equals 3 columns. We would first shift X to its mean by subtracting from each column the average of that column. We would then calculate the scatter matrix of X, which for this example would give us a 3 by 3 matrix. After the eigen decomposition of this scatter matrix, we would obtain the eigenvectors, which is exactly the transformation matrix we would use to transform X into Y. I would like to note that the eigen decomposition of the scatter matrix is not the only mathematical solution to find the principal components. Other methods to find the principal components include singular value decomposition and expectation maximization. In the singular value decomposition method, rather than first finding the scatter matrix, we directly decompose the data matrix. The components we get from this method are as follows. Sigma is a diagonal matrix similar to the eigenvalues we described before, except the values are now square roots, so these values are the standard deviations rather than the variances of each of the basis vectors. The matrix U is equivalent to the eigenvector matrix we described before, and it is the transformation matrix P that we would use to multiply X with. Principal component analysis method is available in most programming languages. You will most likely be calling a function that takes care of the calculation of the principal components and gives you the transformed data. But it is important to understand how those functions derive the transformation matrix and what their output mean. You may be saying to yourself, we can transform the data into a new coordinate system where the basis vectors are not correlated. So what? How do we use the transformed data for visualization or data reduction purposes? Let's look at a 2D data set. Not only do we get the transformation matrix, which is a 2 by 2 matrix of eigenvectors, but we also get the eigenvalue matrix, whose diagonals represent the amount of variance along each of the eigenvectors. The eigenvalue that is larger would have the larger variance. So if this one were 10 and this one were 5, V2 would be the larger variance. After we find the eigenvectors and eigenvalues, we typically rearrange the columns of the eigenvectors such that the largest eigenvalue is listed first. That would of course mean we rearrange the columns of the transform matrix as well. This rearrangement does not affect the main property that the columns of Y are independent variables. Assuming that we have already rearranged the eigenvalues from largest to smallest, we call the first column of P the first principal component, and the next one will be the second principal component, and so on. The first principal component represents the direction of the largest spread in the data set. The next principal component is orthogonal to the first one and would represent the direction of the next largest spread in the data set. The transformed matrix Y will have two columns. The first column will be the value of each point on the principal component 1, and the second column will be the value of each point on the second principal component. When we plot the transformed matrix Y, we essentially get a rotated and stretched version of the original figure. Here is the important part. Because we have rearranged the principal components so that the one with the largest variance comes first, we know that the first column of Y contains the values of the points along the highest spread. So if we threw away the second column of Y, we would not lose much information. Or to be more technical, most of the variance in the original dataset is captured in the first principal component or the first column of Y. If we show the transformed data as points only on a one-dimensional line, we would not have lost much information. Except looking at points on a one-dimensional line is not very pleasant because the points stack on top of each other. Let's now consider a three-dimensional dataset X, and again assume that we have already arranged the eigenvalues from largest to smallest, making the principal components also ordered according to the largest to smallest variance in the dataset. We can use the transformed data in its entirety, which is not very interesting. We can throw away the last column of the transformed data and show the samples in a two-dimensional plot. Looking at this 2D plot, we can be confident that we are looking at a figure that is a good representation of the original three-dimensional figure. We'll discuss how good of a representation it is in a minute. Similarly, we can throw away both the second and the third columns and only keep the first column. Even though it is not pleasing to show the data in one dimension, being able to summarize a three-dimensional dataset in one dimension can be numerically very useful. I hope you can see where I am going with this. If we have a high-dimensional dataset, it can have 100 columns or 1000 columns, it doesn't matter. We cannot really visualize the data in such high-dimensional space. And if we plotted only the first 3 columns of X, or any arbitrary 3 columns of X or 2 columns of X, we would likely grossly misrepresent the samples. But after transforming the dataset using principal component analysis, we are confident that the columns of Y are ordered according to how much variance or spread they capture from the original dataset. We can plot this transformed matrix using its first 3 dimensions or its first 2 dimensions. Using 2 dimensions is typically what we do. Another common visualization task we may perform is when the original dataset contains samples obtained from different groups. Let's say we have collected gene expression values of some samples. Here each column represents a different gene and each row represents a different sample. And let's say we have 3 breast cancer samples shown in green, 3 ovarian cancer samples shown in orange, and 3 prostate cancer samples shown in purple. When we transform the data and plot its first 2 columns, we can show different groups using different colors or labels to help visually investigate whether samples coming from the same cancer type have similar expression values, as would be reflected by them clustering together. Let's revisit the question of how good of a representation we get after we throw away some of the columns from the transform matrix and keep only the first few. Let's consider a 4-dimensional matrix X. The eigenvalue matrix is a diagonal matrix where each of the diagonal values is the variance of one of the principal components. You can see that I have already arranged them from largest to smallest. We know the first principal component has the largest variance, but how large is it compared to the others? To quantify the relative magnitude, we can just add them all up, which gives us 20. The first variance has 12 over 20, which makes up 60% of the total variance. The second variance has 6 over 20, which makes up 30% of the total variance. Together, the first two principal components make up 90% of the total variance in the dataset. Having this information now, we can get a sense of how representative or good a two-dimensional representation is. We look at how these points are spread out in 2 dimensions, and we know that what we see represents 90% of the way that these points are spread out in the original 4-dimensional space. When you see a 2-dimensional representation of a high-dimensional dataset like this, you must ask yourself, how much of the variance am I capturing in these first two principal components? If I show you a 2D figure and don't tell you how much of the variance it is showing, it doesn't matter how well these groups are clustered, because it may not be representative of how the samples are related to each other in the original dataset. It is therefore of utmost importance that when you produce a PCA plot, you label your axes with how much variance they capture. Here, for example, I have labeled the x-axis as PC1, 60% of the variance, and y-axis as PC2, 30% of the variance. You must do something similar when you are creating your own PCA plots. A concept related to how good a reduced representation is the reconstruction error. What does it mean to reconstruct the data? Remember that y was obtained by multiplying x with p. We should therefore be able to obtain x back by multiplying y with the inverse of p. And remember that P is an orthogonal matrix, which means the transpose of P is equal to the inverse of P, allowing us to write x equals y times the transpose of P. Reconstruction takes us back from the principal component space to the original coordinate space. What happens if we threw away some of the columns of y and only kept the first k of them? We can again reconstruct the original space with this partial information. Because we threw away some of the columns of y, the reconstruction will only be an approximation. We will not get the original x values. We can quantify the reconstruction error by looking at how different the numbers in the approximation are from the original data matrix. The reconstruction error is closely related to the amount of variance we had captured in the first k components. If, say, the first k components capture 99% of the variance, then we can say that the numbers we get in the approximation should be fairly close to the numbers in the original matrix. To summarize this lecture, principal component analysis is a linear transformation method that can be used to reduce from a high-dimensional space to a smaller number of dimensions. The dimensions in this new space are ordered by how much of the variance in the original data they capture. We can use the first 2 or 3 dimensions of the transformed matrix for visualization purposes. We may keep more dimensions when we are making use of this data in some of the other analysis tasks.